All right, let's go ahead and we're going to do our last problem on our basically exam, our phase diagram. So let's go ahead. We'll fill out all the sections of the phase diagram. So this is FCC, so that's going to be FCC plus this. This is going to be liquid plus this. And we're going to go liquid plus this again. Liquid plus this phase here. Here's this phase plus this phase plus this phase. And here plus this, liquid plus this, liquid plus BCC, and then this plus BCC. Again, you could do that much more thorough with numbers and all that good stuff. Excellent. So fill out the section's phase diagram, congruent melting points, and invariant points. So let's go ahead. Our invariant point, maybe something like right here, here. Any other congruent melting points? Congruent melting point are also right there. Fantastic. What about some invariant points? Eutectic here, peritectic here, liquid plus solid to a new solid. That's another peritectic because liquid's involved. Peritectic. Anything else? Nope, that's pretty much it. Fantastic. So we've got those done. Let's look at 0.6 NB. 0.6 NB at 100 degrees centigrade. So let's say it's just like right here. So right here. And what are we asked? What are the phases, components, composition, fraction, chemical potentials, and degrees of freedom? So my degrees of freedom expression, first of all, there are two phases, alpha, and then this one. I'm going to call this P1. I'm going to call this P2. So I'm going to say that P1, excuse me. So the degrees of freedom plus phases, which are 2, equals components plus 1. Components are 2, AL and MB. So my degrees of freedom is equal to 1. If I'm in a two-phase region, I know that my chemical potential of P1 is equal to my chemical potential of P2. Excellent. My composition of P1 at this temperature, at this composition, I'm going to run over here, and that's going to be at 0.5. My composition in P2 will be equal to about, let's call that, 0.65. Right? Yeah, exactly. 0.65. My fraction in P1 will be equal to, in the denominator, remember, it's the full length. So 0.65 minus 0.5. And I'm going to run opposite. So I'm going to go 0.65 minus 0.6. Because that's where our initial composition is. The fraction in P2 is going to be equal to, denominators is still the same, total length of my line, 0.65, and then finally we're going to run opposite, so it's going to be 0.6 minus 0.5. And that makes sense. We're closer to phase 2, so the fraction is larger. Excellent. Excellent, we got it. And then finally, draw the free energy at 1750. So let's just draw it right in the middle there. We'll go across. Let's sketch this out. Sketch this out here, sketch this out here. All right, so what I'm going to do, I'm going to switch colors here. Oops. Let me go to my drawing. I'm going to go to black here for a second because what I want to do is I'm going to draw, and this is, again, free energy, XB. So I'm going to draw a dashed line every time we cross over to one of these lines. So this is a little bit tricky here. Ooh, a little region. Little region. Oh, I'm getting a little bit. It's okay. All right, so what I'm going to do is I'm also going to go ahead and right now, and I'm going to say, obviously liquid is liquid. I'm going to also say this is going to be my P1. This is going to be, let's go red. I'm going to call this my P2. And I'm going to call this, not that one. I'm going to call this, nope, I did that already. Let's do this. I'm going to call it P3. So when we're looking at this, first, we're just pure liquid. Then we're liquid plus P1. Then we are pure P1. Then we are P1 plus P2. Then we are just P2 here, and then we are P2 plus P3, and then P3 over here. So I want to draw a common tangent everywhere I have a two-phase region. That's just a P2. This is a P2 plus P3, and then there we go. So I'm going to get my colors. So I'm liquid. I'm just hanging out. I'm now in a two-phase region, and now I'm exiting. Let's go to our orange color. Here, I got to be higher because lowest free energy wins, but now I'm in a two-phase region. Now I'm hanging out, but now I'm also in P1 plus P2, so I have to hit this, and then I escape. Let's go to red. Same thing. High. I have to touch this two-phase region. Now I'm just kind of hanging out, and then I have to touch here, and then I'm escaping, and then finally P3, similar scenario. And then I'm just hanging out. We can double check at each region to ensure that we are seeing this. And remember, our chemical potential is equal to dG dN at constant temperature and pressure. And that is just the slope here. So those are the common tangents. Hence, in a two-phase region, two phases must be equal, chemical potential must be equal, common tangent. Thanks, and I'll see you in the next video. Bye.